Welcome to Study Loop.
Hello, today we're doing problem 9.54, and this gives us this reaction scheme saying that we start from this starting material, which they call V, and when you react it with alkyl and pyridine, we get the alkene elimination product, W. But why is it that when we react it with H2SO4, we get an isomeric mixture of three products, X, Y, and Z? And it asks us to draw the stepwise mechanism for each reaction and explain why the difference occurs. So if we remember the reaction mechanism of alkyl and pyridine, elimination will occur through an E2 mechanism. So your nucleophile will attack when you're at the same time as your alkene forming at the same time as your leaving group leaves. So that means that it's three arrows all in one step. And because of that, you can't really do any carbocation rearrangements. You don't even have a carbocation intermediate. So that explains why we only get this one product. Conversely, when we use a strong acid such as H2SO4 sulfuric acid, we go through an elimination through an E1 mechanism. So a carbocation intermediate is formed, and because that carbocation intermediate is formed, we can do hydride shifts or R shifts to generate the most stable carbocation possible. So if we have a secondary carbocation, we can do a proton a hydride shift or a R shift to make a tertiary carbocation, which would be more stabilized due to its inductive stabilization. So let's begin with the mechanism of alkyl, and we'll understand why we only get this one product. So if I redraw alkyl, we see that we have an electrophilic phosphorus atom here, and obviously in our alcohol we have a very good nucleophile being this oxygen. So we can show the nucleophilic attack to pop off one of these chlorine atoms, giving us our intermediate. And remember, pyridine is used as our proton mop. So this proton here will be deprotonated by pyridine to just neutralize everything and help the reaction go to completion. So now we made a very good leaving group from this bad leaving group that we started from. So because of that, we can do our elimination step. And from our elimination step, we need to identify where the beta carbons are. So obviously, the carbon that is bound to our leaving group is called the alpha carbon. So the carbons right adjacent to that are called beta carbons. So we see we have two beta carbons. In order to do our elimination reaction, we need to find the beta protons. So on the right, we already have four functional groups. So there's no protons on this beta carbon. However, here we have two equivalent protons that can be used for this elimination. So another molecule of pyridine will be used at this point. The nucleophilic nitrogen will attack and picking up this proton, making a bond. When you make a bond, you break a bond. So that sigma bond will break to form your alkene. Now we made a new bond. So therefore, when you make a bond, you need to break a bond. So our good leaving group will leave. So as you see here, three arrows all in one step. And this gives us our single elimination product. However, if you were to use a strong acid, such as sulfuric acid, I'll just call this HA for simplistic sakes. We see that first, just like before, our nucleophile, being this alcohol, will be protonated by our acid, giving us protonated water. And remember, Oxygen does not like to have a positive charge. It either likes to be neutral or negative. So because of that, this water will spontaneously fall off. And now we have a secondary carbocation. But as you can see here, if we do an R shift using this methyl group, we can get a tertiary carbocation. So tertiary carbocations are more stable than secondary carbocations due to the inductive stabilization of its substituents. So from this point, we need to identify beta and alpha carbons. So obviously the carbon where the carbocation is on is our alpha carbon. So all the carbons that are right adjacent to it, right next to it, are beta carbons. So we see that we have 3 beta carbons, and each of these beta carbons have beta protons that can be used for deprotonation and elimination. Obviously, we also generate our water here at this step. So because we generate this carbocation intermediate, that is why we can get an isomeric mixture of products. So we use this H plus to protonate the water, to generate this water. So now we have an A minus floating around that can do deprotonation. So that's 3 options to do. Again, you pick up this proton, making a new bond. When you make a bond, you break a bond. So this bond will break. So this is option 1. When that bond, those 2 electrons of the sigma bond come down here to form your alkene, this carbocation is neutralized because it regains its 4 bonds, maintaining the octet rule. So this generates a tri-substituted alkene. We have 1, 2, 3 functional groups. Alternatively, this A minus can pick up this proton to form an alkene over here. And this forms a tetra-substituted alkene, which is more stable and going to be a major product compared to this tri-substituted style alkene. Or lastly, you can pick up this proton here to form the alkene over there. This also forms a tetra-substituted alkene. So this explains our 3 products, Y, Z, and A, and X. Obviously, in all 3 of these cases, we have a plus HA, so we reform our acid catalyst. So this is an acid catalyzed elimination reaction.